learners. Last time we talked about what happens to either a solid or a liquid when it is heated, and we noted that if a solid or a liquid is heated, what happens is that it changes its state. Its temperature increases, and just in case it reaches its boiling point, then you expect it to change its state. If it was a solid, maybe from a solid to a liquid. If it is a liquid, from a liquid to a gas. And again, the reverse happens during cooling, that you have some gas and then you cool it. You expect the gas to change from its state to a liquid. And if it is a liquid and it is being cooled, it will change from a liquid to being a solid. So under Form 1 work, that is particulate nature of matter, we gave different names for different changes of state. Like from a solid to a liquid, we called that melting. Liquid to a gas, vaporization. A gas to a liquid, do I still remember? A gas to a liquid, okay, I think you can fill that gap. From a liquid to a solid, it is freezing. What about a gas to a liquid? What about from a gas to a liquid? You people, you can feel that on your own. So basically, what you are saying is that when a solid is heated, its temperature rises. When it reaches the melting point, it melts. During melting, there is no temperature change because the heat supplied is used to break down the forces holding together the molecules of the solid. So just in case you are carrying out an experiment, you have your thermometer there, and then you are heating a solid, and you are registering the change in temperature. You will notice by the time the solid reaches its melting point, there is no change in temperature. Why? There will be no change in temperature because the heat that is supplied to a solid when it reaches its melting point is used to do what? In the process of melting. Or in other words, it is normally used to break down the forces holding the molecules together. Remember something from Form 1 work, that particles of matter are normally held together by the cohesive forces. And the heat, because the heat that is absorbed is never registered on a thermometer, or rather it doesn't lead to a change in temperature when a substance is changing its state, either from a solid to a liquid or a liquid to a gas. That heat is referred to as latent heat. Latent means hidden. Latent heat. So we have the latent heat that is used for melting, and there is also the latent heat that is used for vaporization. The latent heat for vaporization, the heat that is used to change the state of a substance from a solid to a liquid is referred to as latent heat of fusion. Latent heat of fusion. That is if you have a substance changing from a solid to a liquid. And then from a liquid to a gas, that is latent heat of vaporization. I want to make it very clear. Latent heat of vaporization can refer to the heat that is supplied, or rather required, to change the state of a unit mass of a substance, not really unit, a mass of a substance from a liquid to a gas without changing temperature. And even if it is changing from a gas to a liquid, that amount of heat that is required is still known as latent heat of vaporization. And also, even if we have a substance changing from a liquid to a gas, the amount of heat required for such is still known as latent heat of fusion. So we talk about latent heat of fusion when you have a substance changing from a solid to a liquid or a liquid to a solid. And we also talk about latent heat of vaporization when you have a substance changing from a liquid to a gas or a gas to a liquid. I hope that is clear. So the first thing I would like us to handle is what we refer to as the latent heat of fusion. The latent heat of fusion, this is defined as the heat required to change the state of a material from a solid to a liquid without temperature change. the converse also applies. What does it mean? That we can have the latent heat of fusion now when we have a material changing its state from a liquid to a solid. Maybe you have some ice, and then you heat this ice, and the ice changes to water. The amount of heat that you'll have supplied to that ice, or rather the amount of heat that will be used to melt the ice, is what is referred to as latent heat of fusion. And again, if you are having water and then you are cooling the water is expected to change to ice at mostly 0 degrees Celsius. The heat that will be supplied to change now the water back to ice is still known as what? Latent heat of fusion. So there is a curve that they have provided for us, and that is the cooling curve of naphthalene. I think on the x-axis we are supposed to have time, temperature, a graph of temperature against what? Time. And we are seeing that at O, naphthalene is in a liquid form. So when it is cooled, it reaches a certain temperature, that is its melting point, whereby now naphthalene does what? Changes from a liquid to a solid. And then when the solid now continues to do what? To cool. So from O to P, naphthalene is in a liquid form. PQ, that is the time from P to Q, that is the melting point, or rather the time between P and Q, the time that is used for what? Melting. And then QR, that is where we have our solid, its temperature just reducing. So many times you can be given a curve like the one that you are having for OPQR, and then you are asked to calculate the specific heat capacity of the liquid. Specific heat capacities, we've talked about them, whereby we say that the specific heat capacity of water is it 4200? Yeah, 4200 joules per Kelvin kilogram. So if you are given this curve, you should be in a position to do what? To calculate the specific heat capacity of the liquid. So when you are supposed to calculate the specific heat capacity of the liquid, you are expected to use what? The path OP, because it is at OP alone that we have the liquid form. And I'll give you a question, or instead of giving you a question, you can go to my YouTube channel, Mildred Wanatia, and look at what I've discussed for the Form 4s about the quantity of heat. It is already uploaded. And then there is PQ. PQ is the point where this substance is melting. So at PQ, if you're asked now to calculate the specific latent heat of fusion, this is the path this is what you're supposed to use, because melting is appearing, or rather happening at PQ. And the other section can help you in calculating the specific heat capacity of the solid. And I'm kindly requesting that you log into my YouTube. I'll give you the link for the same. And look at the question that I've done for the Form 4s. I've just written that topic as the quantity of heat. I've uploaded a number of videos there. The videos, most of them, actually all of them are Form 3 work. Is there an exception? Yeah, most of that work is a Form 3 work, so it can still help you. The topic is a revision, and then I give the subtopic. They are very short videos. They not take a lot of your time. So kindly for the solution of that, you are supposed to use that link for you to be able to calculate specific heat capacities, and also specific heat capacities, and also specific latent heat, which could be of fusion or vaporization. So the next one is the specific latent heat of fusion. We've already defined specific latent heat of fusion as simply the quantity of heat required to change a material from a solid to a liquid without change in temperature. But now when we introduce there the word specific, then the definition changes. Now if it is we are talking about specific latent heat of fusion, this is the quantity of heat required to change a unit mass. take note, unit mass. Specific, the word unit mass must be mentioned. This is the quantity of heat required to change a unit mass of a material from a solid to a liquid without change in temperature. And Q is normally given as MLF, where LF is the specific latent heat of fusion, M is the mass, and Q is the quantity of heat that will be supplied during a certain experiment. So, in most questions, LF will always be given. The mass, of course, we know what that is. And then you should be in a position to calculate the quantity of heat. And remember from the previous questions, the quantity of heat, we've been calculating them. If it is electrical, we are using the formula power times time, or simply the VIT. And if it is being done manually, maybe you have some ice and the ice is put in water and the ice melts and the temperature changes, then there are also some formulas that I gave to you that you should be in a position to use. So I'll only do one example here on the specific latent heat of fusion, and I would like us to read the question together. Let's go. In an experiment to determine the specific latent heat of fusion of ice, take note of those values. In an experiment to determine the specific latent heat of fusion of ice, 0.025 kilograms of dry ice at 0 degrees Celsius is melted up in 0.20 kilograms of water at 21 degrees Celsius in a copper calorimeter of mass 0.25 kilograms. Very important, the values. If the final temperature of the mixture falls to 11 degrees Celsius, what is the specific latent heat of fusion of ice? We've been given take the specific heat capacity of water as 4,200 joules per kilogram Kelvin, and that of copper is 400 joules per kilogram Kelvin. I repeat the question. Anytime you are given a question, remember to read it more than once for you to be able to understand what the question is all about. And the question reads, in an experiment to determine the specific latent heat of fusion of ice, 0.025 kilograms of dry ice at 0 degrees Celsius is melted up in 0.20 kilograms of water at 21 degrees Celsius in a copper calorimeter of mass 0.25 kilograms. You could be noting some of these things down to avoid confusion. You can have the quantities representing water, the quantities representing ice, and there's also the copper calorimeter. So if the final temperature of the mixture falls to 11 degrees Celsius, what is the specific latent heat of fusion of ice? So for such an experiment, you just have to know what are some of the heat changes that are taking place in this experiment. So we have ice, and this ice is at 0 degrees Celsius, and this ice is being dropped into water that is at 21 degrees Celsius. So ice being at 0 degrees Celsius, we expect the ice to absorb heat from the water that is at 21 degrees Celsius. So when ice absorbs heat from the water at 21 degrees Celsius, the water now will be losing heat. The water will be losing heat. Again, the water is within a calorimeter. The calorimeter is also expected to do what? To lose heat, because the heat of the calorimeter depends on the heat of the water. It is like when you have a cup and then you put there some tea. The cup normally becomes warm. The temperature of the cup and the temperature of the tea becomes the same. So if you're having a calorimeter, then when the temperature of the water falls, also the temperature of the calorimeter falls. So in a nutshell, what I'm saying is that the water will lose heat, and also the calorimeter will lose heat. Ice, which is at 0 degrees Celsius, will gain heat. But because it is already at its melting point, the temperature of the ice will not increase fast. The ice will gain heat. First of all, the heat will be used for melting. And after it has melted, the water that will be formed from ice will also be at 0 degrees Celsius. So the water formed from ice will also absorb some heat, and its temperature will change. In fact, the question tells us that the temperature of the mixture falls to 11 degrees Celsius. So at the end of the experiment, the temperature of the water that was in the calorimeter will be 11. The temperature of the calorimeter will be 11, and the temperature of the water formed from ice will also be at 11. So the question is asking us, where is the question? If the final temperature of the mixture falls to 11 degrees Celsius, what is the specific latent heat of fusion of ice? So as long as you've already noted what will be absorbing heat and what will be losing heat, you straightly go to calculations. Where have I done my calculations? Here are the calculations. In fact, this is an example from the textbook. So for the solution, you do the heat lost by the calorimeter first, and the heat lost by the calorimeter is simply the mass of the calorimeter times the specific heat capacity of the material making the calorimeter times temperature change. Whatever we are referring to as Q is equals to mc theta. So the mass of the calorimeter is 0.25 kilograms times 400 times 10. So the heat lost by the calorimeter is 1,000 joules. You do the same for the heat lost by the water. The water within the calorimeter was 0.2 kilograms. You multiply by C, the specific heat capacity of water, then theta. 0.2 times 4200 times 10, that is 8400 joules. And then heat gained by the melting ice, you simply use MLF. So we just have the mass and we don't have L. So L remains to be our unknown. And then heat gained by the melted ice, the water that will be found from the ice after melting will still have the same mass as the ice. So you use Q is equals to mc theta. The mass of the ice was 0.025, and that is also the mass of the melted ice, times 4200. It is no longer ice, we use 4200 times the change in temperature, which is 11. Where are you getting the 11 from? 11 is from the final temperature, which is 11 degrees Celsius, minus the initial temperature, which is 0 degrees Celsius. And then we substitute this into the equation. Heat gained is equals to the heat that is lost. So you pick the values that you've obtained here, and then you form an equation, then calculate L. So when you get L, that one becomes the specific heat capacity, specific latent heat of what? The ice. I hope it is understood. In case of a question, kindly you can call, SMS, or WhatsApp my number. And then as an assignment, book 3, revision exercise number 6 should be enough for you. Do the work, post in the working, and I wish you all the best throughout the term.